Imagine a computer so powerful that problems taking today's supercomputers thousands of years could be solved in minutes. A machine that doesn't just calculate, but explores possibilities all at once. Welcome to the strange and beautiful world of quantum computing. Now picture this: information not stored as simple zeros and ones, but as shimmering states that can be 0, 1, or both at the same time. Logic that bends. Probability that becomes a tool. Computation that feels less like marching through instructions and more like diving into a vast ocean of parallel realities. In this realm, the encryption methods we rely on today begin to look fragile. Optimization problems that once seemed impossible suddenly open, like unlocked doors. Chemistry, materials science, climate modeling, all stand on the edge of a revolution powered by particles dancing to the rules of quantum mechanics. It's not science fiction. It's the next frontier of computing, a frontier where intuition breaks, imagination expands, and the limits of what machines can do are rewritten. And we're only at the beginning. Quantum computing is a new kind of computing that uses the rules of quantum mechanics, the physics of the tiniest particles in the universe. While classical computers rely on bits, zeros, and ones, quantum computers use qubits, which behave in ways that defy our everyday intuition. Qubits can exist in multiple states at once, a phenomenon known as superposition. Instead of choosing between 0 or 1, a qubit can be a blend of both, like a coin spinning in the air rather than resting on heads or tails. And when multiple qubits interact, they can become entangled, forming deep connections that let them influence each other instantly, no matter how far apart they are. These strange behaviors give quantum computers a kind of parallelism that classical machines simply can't match. They can explore countless possibilities simultaneously, making them incredibly powerful for certain tasks, from simulating molecules to optimizing complex systems to breaking cryptographic codes that protect today's digital world. Quantum computers won't replace classical computers, but they will transform the kinds of problems we can solve. They represent a shift from deterministic logic to probabilistic exploration, opening a new frontier where physics and computation merge in astonishing ways. A classical bit is simple. It's either a 0 or a 1. But a qubit can be both 0 and 1 at the same time, thanks to a quantum property called superposition. This means a quantum computer can explore many possibilities simultaneously. Even more mind-bending is entanglement, a connection between qubits so strong that changing one instantly affects the other, no matter the distance. Entanglement lets quantum computers process information in ways classical computers simply can't. When superposition and entanglement work together, the computational landscape changes completely. Instead of processing information step by step, a quantum computer weaves together countless states and relationships at once, creating patterns of possibility that classical machines could never generate. It's less like flipping switches and more like choreographing a synchronized dance of probabilities. This is why quantum computers hold such promise for problems involving enormous complexity. Tasks like simulating molecules, optimizing global systems, or cracking mathematical puzzles that stump even today's fastest supercomputers. They don't just compute faster, they compute differently, tapping into the strange rules of the quantum world to reveal solutions hidden from classical logic. And while the technology is still young, each new qubit, each new breakthrough brings us closer to machines that operate on the very fabric of reality itself. Because qubits can hold multiple states at the same time, adding more qubits increases computing power exponentially. 2 qubits can represent 4 states. 3 qubits can represent 8. 4 qubits can represent 16, all simultaneously. This built-in parallelism is why quantum computers could eventually solve problems that classical computers would need thousands of years to complete. As the number of qubits grows, the system's ability to explore huge solution spaces grows with it, not slowly, but explosively. With only a few dozen qubits working together, a quantum computer can represent more possible states than there are atoms in the observable universe. That's the scale of computational richness we're dealing with. This doesn't mean quantum computers will instantly solve every hard problem, but it does mean they can approach certain challenges, like simulating complex molecules, optimizing massive networks, or analyzing enormous datasets, in ways classical machines simply cannot. Instead of checking possibilities one by one, a quantum computer begins with a universe of possibilities already in motion, then uses quantum algorithms to guide that universe toward the right answer. Quantum computers aren't faster at everything. but they shine in very specific domains. They're exceptionally good at simulating molecules and materials, a skill that's crucial for drug discovery and advanced chemistry. They can uncover patterns hidden inside complex datasets, helping fields like biology, finance, and large-scale optimization. They're also powerful at factoring large numbers, a task closely tied to modern cryptography. And because they operate under the same quantum rules that govern nature itself, they can model physical systems with remarkable accuracy. They're not meant to replace your laptop or your phone. Instead, they're built to tackle the hardest, most intricate problems in science and industry, the kinds of challenges where classical computers struggle and where quantum mechanics opens entirely new possibilities. As the technology matures, quantum computers could help design new medicines by predicting how molecules behave before they're ever created in a lab. They could optimize global logistics networks with millions of moving parts, making transportation, energy, and manufacturing far more efficient. They could accelerate breakthroughs in climate modeling, materials science, and even artificial intelligence by exploring solution spaces far too vast for classical machines. Quantum computers are incredibly delicate. Qubits lose their quantum state when they interact with the environment. This problem is called decoherence. To prevent it, quantum machines must operate at temperatures colder than outer space. They rely on advanced error correction techniques. Building stable, scalable quantum computers is one of the biggest engineering challenges of our time. Even the slightest vibration, stray photon, or electromagnetic fluctuation can disrupt a qubit's fragile state. That's why engineers isolate quantum processors inside elaborate shielding systems. These systems are cooled by powerful cryogenic refrigerators, bringing them within a fraction of a degree above absolute zero. At these extreme conditions, qubits can maintain coherence long enough to perform meaningful calculations, but only with the help of sophisticated algorithms that detect and correct errors faster than they appear. The challenge isn't just keeping one qubit stable. It's keeping hundreds or thousands stable at the same time, all working together in perfect quantum harmony. Achieving that level of control requires breakthroughs in materials science, physics, engineering, and computer science. It's a frontier where every improvement feels like a small miracle. Yet progress is accelerating. Each year brings longer coherence times, better qubit designs, and more reliable quantum processors. The path is challenging, but the potential rewards, new medicines, new materials, new insights into the universe, make the effort one of the most ambitious technological quests of the century. Even though quantum computers are still in development, progress is accelerating. Researchers believe that in the coming years, quantum machines will reach a point where they can solve meaningful, real-world problems faster than classical computers. That milestone is called quantum advantage. Quantum computing isn't science fiction. It's the next frontier. And every breakthrough brings that frontier closer. Each improvement in qubit stability, error correction, and hardware design pushes quantum systems from fragile lab experiments toward practical tools. What once required entire rooms of equipment is slowly becoming more compact, more reliable, and more scalable. The field is shifting from theory to engineering, from possibility to implementation. As these machines mature, they won't just speed up existing tasks. They'll unlock entirely new ways of solving problems. They'll help scientists design new medicines, discover novel materials, optimize global systems, and simulate the fundamental processes of nature with unprecedented precision. Quantum computers represent a shift in how we think about computation itself, expanding the boundaries of what technology can achieve. We're witnessing the early stages of a technological revolution, one that will reshape science, industry, and our understanding of the universe. Thanks for watching, and I'll see you in the next chapter of this digital adventure.